Mm. So the decision tree, the R part in R has two algorithms. One is to grow a tree. Another is to prune that tree. The tree in R part will grow until one of the three criteria is met. And those three criteria are controlled by three parameters that the user can provide. The first is when we grow the tree, we know adding nodes will always going to improve tree's performance on the training example. So there is a parameter that controls how much of the decrease in error that we want that branch to improve when we grow the tree. So this is what they call CP, cost complexity. And the number of samples in the node, the minimum number of samples in the node is another parameter that we could control. If the number of samples dropped below this threshold, the tree will not grow off this node. This node will become a terminal node. The third attribute is the tree depth. We can control how deep we want the tree to grow. We mentioned earlier, deeper tree going to be more accurate, but it could also risk overfitting. So this is max depth that we control. Those are all hyperparameters the user are going to provide. The book, the data mining with R book comes with a package. It provides this function, R part XC. This combines these two methods. So you build a tree and then prune it using this function. Therefore, this function has a combination of the parameters used for both R part and prune.R part functions. Those are the basic functions that we're going to use today. So I'll just make sure that I have all the libraries loaded, and we're going to load our police shooting dataset and look at our attributes, and we can decide what attributes to remove. So we're going to remove those continuous valued attributes, and also the attributes have very high cardinality. So I decided to remove ID, name, date. Armed is removed because we have armed group, armed type already. Age is removed because we have age group. City is removed because of high cardinality. State removed because of high cardinality. VP ratio is removed because it's real value. VP ratio, we have actually VP ratio level, a discretized variable. So I think our data set still represents much of the information in the original. So after remove those, we get a smaller.
Sorry, Professor, what was VP ratio again? I forgot.
Yes, no worries. Go ahead.
For VP ratio, I'm sorry, I forgot.
Yeah. VP is our victim population ratio.
Thank you.
Yeah. So after we discretize some of the things and removed some of the information with high cardinality, we could actually, our cleaned data set may actually end up have duplicate rows, right? So we need to remove those. First, let me check how many of those rows are duplicate. We have 107. Then we need to remove those duplicate rows. So those rows.
I had a question about duplicates. Yes. Isn't it valuable to keep it to know that this occurs more frequently, or doesn't help because it doesn't generate a new rule?
For decision trees, those duplicate information will not. Well, actually, it does. What I worry is that the data set could have exactly the same attribute but have different labels.
Okay, so if the outcome is different, but the inputs are all the same, then it's confusing to the
Yes,
decision tree. Okay.
right. I discovered there's duplicate value is exactly because when I use a fully grown tree to classify the training example, I got a low performance. It's not 100%. So I went back and checked. I realized, oh, those duplicate values create this problem. So after we remove those duplicate, if all the values are duplicate and the labels are unique, then you should keep them. It does give you true distribution of the data. We don't want to remove data without a reason. Here the reason that I remove those duplicates is because they could have different labels.
So in this case, I didn't quite understand what line 53 is doing. So I understand that when you do not duplicate it, it means it will keep unique rows. But then when you do accept that column, what is the meaning of accept that column and duplicate it? That means how is that? Like it's taking duplicates calculated on all other column combination?
No, the duplicate is identified on the other columns, not race. So here what we did is give me this shooting data set after you removed column 3, after you remove race 3.
So it's basically saying find duplicate, like let's say we have 3 columns, A, B, and C.
Right.
Then if we are looking for duplicates with A, B, C, we are going to find fewer duplicates. But if we look with only A and B, like we exclude C, then we're going to find more duplicates because C could have been what was unique between 2 rows. So like you could have A1, B1, and C1, and A1, B1, C2. But if we remove C, then A1, B1 by itself is duplicated. So does that mean that we're essentially saying that if we have the same values on variables or factors, but they give you different races, then that is confusing for our model? These might be outliers. That's why we're removing it? Or
yes, exactly. What we're trying to do is to remove situation like this. So this will not be duplicate because when we consider race, they may not be duplicate. But if we exclude the label, just look at the data itself, the attributes are exactly the same. Basically the same instance, you give them different labels. Those labels are in conflict with each other. Basically, you're saying that this person is black and white at the same time. This is the situation that we want to avoid. This is also a type of noise that we talked earlier, the noise in the label. The label has been inaccurately applied. In this case, the labels were not inaccurately applied. This situation was created because we discretized, we removed some of the differentiating characters for our decision tree demonstration. Does that make sense?
Here, the repeated data are removed that have different labels.
Right. Okay. So this is a factorization method that we're going to use later for random forest. I'm not sure we're going to get to there today, but let me first run it. All it does is just to turn those categorical attributes into factors. It doesn't change anything, the data value or anything else. And I also made a function get score. What this one does is it computes the accuracy score for a model. So we have, if you give a model and the data, we use this model to predict the class label, and then we compare the predicted class label with this test data's label, and then we compute the accuracy. The accuracy is basically the total correct labeled examples divided by total examples. So this return accuracy. So now we can start to train the data, to train a tree. So we use set seeds to make sure that when we run our algorithm with randomness built into it, we will get the same result every time we run it. So we use set seed.
In decision tree, does the randomness come in if there are ties in like the information gain?
It could happen that way. And also when we train the data, that the internally the system does cross-validation. So where samples are selected to be in the training example and the validation example. So every time you run a decision tree using same set of data, you could get a slightly different result. So that's why we use set seeds. And here we use set seeds is because we're actually creating our training and test example. We want to reserve some example for test. So we want to make sure every time we do this, we're going to run using the same training and the same test. This is mainly for you. If when you run it, you will verify some of the results match my results. It doesn't. When you actually do to evaluate an algorithm, you may not want to set the seeds. You probably want to see how system performs given different data sets.
So in this case, would we normally run it like, what is that they call the tenfold process? So that way we get, essentially it's running different seeds. Is that the idea?
No. No, but we will talk about cross-validation today, later. That the seeds is basically saying, okay, this is actually a good point too. So the entire system, a random number generator needs a seed, right? If you give it a different seed, it will generate a different sequence of random numbers. If we use a fixed seed, it will generate the same sequence every time. So if I use, do this. So first now I set the seeds. I say, give me first random number. Give me the second random number, give me the third random number. The system will most likely give me, it will give me a sequence of random number like this, right? I'm just trying to make it random.
Sorry, I guess my question was unclear. I was wondering when you mentioned that when we run it like with like real data, we should not do this because we want to get maybe different values. And I was wondering if that's related to sort of, we want that to prevent the overfitting kind of deal. That's why we do it like cross-validation, or is that something else? Sorry for not being clear.
Well, setting seeds really just want to make sure that in my demonstration, I want to make sure that when you run it, you get exactly the same result as me. In tenfold cross-validation, well, once you set one seed, your 10 cross-validation result going to be the same. If you set a different seeds, you could have a different set of 10-fold cross-validation result. You could do that multiple times to see how cross-validation show the result. But for the purpose of publication, you certainly wanted to, for others to reproduce your work, you want to set a fixed seed. So the key point is, if you want your result to be reproducible, you want to set a fixed seed. Okay, so now we can, with the seed set, we will start to split our data. We did a 75% and versus 25% split on our labeled data. So first I find the, get a random sample of trained row numbers, and using those row numbers to select the training data and the test data.
So, quick question, the sample is without replacement, right? So they
Yes.
won't cause new duplicates.
Yes, those are just one sample. Yeah, this has not, we're not doing cross-validation or bootstrap at all. We're just doing one test. Yeah. So this training set and test set are disjoint. So here we did for this function. I'm going to explain what this does shortly. But for that, we want to see the how the race is distributed. So our Asia, Black, Hispanic, Native, Other, and White has this distribution. And we can look at the level of shooting race. We can see this level is consistent with the sequence. The order of those race are consistent. So now we have the training example and test example. We can build our tree. So here, what I want to do is to use all the attributes that we have in current shooting data to predict race. Our data is the training set. We want to produce a full tree. So we want the tree to grow until there is no gain on the training example. No performance gain on the training example. So CP is 0, gaining. The performance is not increasing. The parameters, we're going to use information gain as our split matrix. We use this you don't have to specify, but I want to explain what prior could be used for. And I have a little example here. I will also post it on your on D2L so that you can verify this. If your data represents the true representation of the population, then you really don't need this. The system will compute the distribution like what we did here. So this is optional. But when you have a situation where your data really does not represent the true population's distribution, you want to provide the true population's distribution here. For example, the system will adjust using this prior probability in the algorithm to make sure to bias towards the class that has high probability in your distribution, for example, here.
So is this because when we had all the data before we remove some columns and before we remove some duplicates, these were the race distributions, and that's what this is building in, or is this just external knowledge from the United States? These are the breakdown.
That's a very good question. Let me think. In our example, I would say it's more of, I don't think it should be the US population distribution. I think it should be the true distribution of all police shooting cases. We may not have collected in our data set all the cases involving police shooting. If you have data that actually reflects all police shooting race distribution, that should be used here. Does that make sense?
Yes, thank you.
Yeah. We set the minimum split to be 2. So if there is 2 elements two elements in the terminal node, you can still split it. So basically, it means split until the leaf node only has one example. Our method is class, it's not regression. So this is how we construct this method call. We run this. So a tree has been built, and we can actually look at the tree, the internal. I will plot this cost complexity graph for you. Let's make it bigger so you can see what kind of information that we can gather from here. Ooh, I think I need to make this screen even bigger and do that again. Somewhere I think I have a, I don't know, what did I do before? We need to split this to, okay, so this is the plot. We can see the tree has over, this fully grown tree have over 1,300 leaf nodes. So size of the tree is measured by the number of leaf nodes. And we can see this is our CP, the performance gain, by adding more and more nodes to the tree. The very last, the fullest tree, when we add the last node, we're not gaining anything in terms of performance. So that's our zero, that's our threshold, the minimum CP. The cross-validation arrow is where we really need to pay attention, because this shows how well the tree is going to perform on real new sets of data. So we can see this cross-validation was dropping, arrow was dropping somewhere here. At this very small tree, the performance is okay. And then the cross-validation keep on raising. The more nodes we put into this tree, the more overfitting we're seeing. So this long tails from starting from here to here, those shows how overfitting is occurring, starting from, I don't know, maybe 8, 10, 6 nodes. And if we actually evaluate out this tree's performance on our training example, we're going to see the tree is very accurate. What did I do? Oh, I forgot to remove, I think. Maybe I didn't run this duplicates. We were only explaining that. And
when we run it, we have fewer size. The size is small.
Yeah. We'll do that. So yeah, the number did match what I had before. So this tree is totally overfitted. Tested on the training example. Tested on the test example, the performance is very, very low. It's only 45, much lower, right? Half of the performance. So so that's the point that I want to show. The next thing I want to show is the pruning. Prune apart is a function coming from rprune. We can just supply this minimum CP for the tree to trim off the points. Internally, what it does is actually exposed here using the function provided by machine learning with R book. So here, the parameter that we can actually specify, this also controls how the tree is pruned. So earlier we talked about when we prune a tree, we actually, the system generate a sequence of nested subtrees of the original tree. And our task is to find the smallest sized tree, but with very good performance. So the idea, this XXE method, X can be replaced with a number, 1XE, 2XE, for example. XE stands for standard error. The idea is when we do cross-validation, we can estimate any of those trees. We can find a tree with the best performance. And its standard error, for example, 4.5 plus minus 0.4. But we could find a smaller tree. It has a little bit higher error. However, if this error is only one standard error away from this minimum error, then we would choose this smaller tree. So you can see the trade-off between the performance and the size of the tree. The reason we want smaller tree is for robustness of the model. We try to avoid overfitting. So this, we can change this X from 1 to 2. If we change this X to 2, then we are okay if this error is greater than 2 standard error away from the minimum error. So this is the idea between the XE pruning. This is used in R parts algorithm that is not exposed. The parameter is not exposed. This R part XE method exposed that, so the user can specify whether I want 1 or 2. So we can redo this tree and generate the tree. I'm not going to run that. Do I have to? Oh yes, probably I do, to show the rest of that. To show, yeah, okay, well, let's run this. Minimum split, I'm asking for 3 now, maximum depth is 3. All those parameters I chose, sort of randomly or arbitrarily. Later, we're going to see how to choose them. So we have this tree now.
I have a question.
Yes, go ahead.
So CP meant that the decision tree should grow until the information gain becomes 0, right?
Yeah.
Okay, so if we want to grow that until it becomes 0, is it possible necessarily when we have the minimum split to be 3? Because to reach the CP of 0, maybe we need the minimum split of 2. Am I right? So which one is?
So any one of the condition is met, the system would stop.
Okay, all right.
Yeah. I did run that. And now we can look at the tree. And this tree is smaller. Okay, so this is a harder way to read a tree. You can still read it if the poverty level and all that. But there are tree plots that we can use to plot the tree. So here, in order to show the comparison of different parameters, there are different parameters that you can adjust for your tree visualization. I'm going to show 4 of those. My preferred one is the last one. You don't have to agree with me, but I just want to quickly show that it's a different visualization of the same tree. Roughly, you can see the last one has the fullest information, more detailed information. So I'll return it back to my. Then we have this this tree. We can use this tree to predict. The performance is not great, but better than 45. And we can get a score on the training. The training score is dropped dramatically from 99.9% to 52. But on the test, our performance has increased from 45 to 53. 53 is not great, but this is pretty much what we can do with this data set. I mean, given our pre-processing steps, there are probably other things we could do. We also tried the Gini index. We got very similar result.
Can I ask a question?
Question. Here, the result on the testing set is better than the training set.
Yeah.
Is that common, or is that is just because I'm just trying to understand how that happens?
It happens because I think this is indication that our tree are not overfitting for now. This is a clear indication that the tree is not overfitted. That the training, the difference is actually pretty small. You probably will run into similar situations when the performance on the tested data is slightly better than the training data. It could also be a sign of under-training. Like this model has not been trained to its full potential. But after we do all those model training, you will see our best model after those tuning, I think it's only 56% something. So based on this information, I would say in this case, this is a reasonable model that we already have.
Thank
this
you.
R-part tree, yeah.
Can I ask a question as well?
Sure, of course.
Oh, great. I think maybe just a little bit of clarification on how I'm understanding the min split parameter, but I thought I remembered that you set min split equal to 3, and it looks like all these trees only have 2 splits.
The min split is the number of the observations in each node, in the leaf node. That is still that. Go back to here, min split. Min split. If the number of the sample in the node is less than this threshold, then we can further split this node. Min split is not how many split the tree has. It's how many examples in the leaf node that would warrant further split.
Oh, that makes much more sense. So then what would the parameter be that could determine the number of nodes that we're allowed to have?
We don't have a way to control how many nodes we can have. The control that we have is CP, minimum speed split, and the maximum depth. We can control how deep we want the tree to grow. We set the parameter to be 3. We want the tree to be 3 levels deep for this tree when we create this tree. So you cannot tell the system, I want the tree to have less than a total of 100 nodes. In this implementation, we can't do that.
Okay, thank you.
Sure. So all those parameters, how do we decide which combination would be the best? We will do a grid search. So this is how we're going to do that. Yes, this is my grid part. So tune a model. Model tuning is typical for any machine learning models because we really don't know which parameters, how to set the parameters. So we just give them all possible values and try different combinations. So this is our hyperparameter grid. We want to try minimum split starting from 2 to 10, maximum depth from 3 to 10. You can certainly change all those numbers. The split algorithm will use information gained and a Gini. So I'll do. So this would give us a total of, we can look at those. So this hypergrid contains different hyperparameter groups that we're going to use to grow our tree. We're going to create a total of 144 trees. That represents all different combinations of the parameters that we have provided. We will declare an empty list that's going to be used to save our trees that's going to be created. So here in this for loop, we loop through our grid and pick out our combination of parameters and use our part to create such model and save the model in this models list. Yes.
So this is just a grid, right? Can we do optimization, or it's too expensive?
What is optimization?
I mean, not just creating a grid, just doing, I mean, in grid, the combinations are, like, how many combinations do we have? Like the steps that it takes?
You can have as many as your computational power supports.
Okay.
Typically, when people talk about optimization, it is a grid search or random search process that the people optimize on hyperparameters.
Yes.
Right. Yeah. So here yeah. As long as your machine memory computational power supports, you can try out a very large range of this. Of grid search. So the grid search, what we did is systematically doing this for every one interval. We're doing this. You could do also randomized, where you actually pick out random numbers. The difference between grid search and random search is grid search does it systematically. Because it does it systematically, so it also runs the risk of overfitting. You could actually pick out a unique combination of the parameter that just does well here. A random optimization search is less so, because you did not do it systematically, but you could also miss certain good combination that's also robust. As we should know by now, there is nothing really determinative in machine learning. You do actually have to try out different things, be aware of different issues involved with different methods. So here what we did is a grid search. We systematically search different combinations in certain range. I think I did the model part. Okay, so we have built this model, 144 models. Let's do those. So you can see this is 49, this is 69, all those models that we have built, saved in this tree. I'm going to ask you to look at one of the models and look at the details of those. So this is one of the model that we learned. So when we give us more information. So this is the function call that we issued. That in this tree, we actually only used 2 parameters to build this tree. Even we gave them over, 20 attributes, only 2 were involved in this tree. At the node level, we have this much of the error rate. The error rate should reduce after that. And then here, this CP table tells you the validation and how the tree was grow. So n split is 0. This is when we have the starting node. We have a cross validation error. This is relative error. I actually did not know what relative error is. I only care about validation error. Validation, it's a 10-fold cross validation, so there is a standard deviation for cross validation errors. When we split this, when we did first split, our error, cross-validation error reduced, and then we did the second split. So you can tell the 1 plus this number of split is the number of the leaf nodes that you currently have. This is a binary tree, by the way. So this gave us some parameters. This is our CP, the performance gain on the training example. So you can see every tree gave us this set of numbers. And we can actually extract those, the cross-validation error and the CP error from each of the model, and then put them together and see which of the 144 trees has the best cross-validation errors. What are their parameters? And that's the parameter we're going to use, that we think that's the best combination. Go ahead.
What are 1, 2, and 3 here? I didn't understand.
Oh, the split. The tree is growing. So
okay,
here,
why do we only have up to two splits? Why not?
Oh, it's because this is a very small tree. I should also draw this tree for you. This is this tree. We only split it twice.
This is one of those grid combinations that we...
Exactly. Yeah, this is one of the 144 trees.
Okay.
Yeah. Those are the functions that from this CP table, we extract the cross-validation for the minimum cross-validation error, we extracted the CP and the cross-validation numbers. So we have two separate functions to do that.
In this output, sorry, I didn't understand, like, I think it's a follow-on question to the previous one. Is each sort of row, when you see 1, 2, 3, there's 3 sort of rows of output? Is that mean that the first number 1 is at the root level, then the next branch, and then finally leaf level, or what?
It's about the split. So this 0 is at the root. And after first split, we split this.
So right? It's the depth of the tree. Each level gets a line. Right.
And then another split. So this table describes to you when we're adding nodes to the tree, how our cross-validation error and how our training error change. Does that make sense?
I had another question. The CP being 0 in row 3, is that because there's no more data after that, or why is CP the information? Isn't CP the information gain?
CP is more complex than information gain. It's basically saying that adding more nodes does not increase the tree's performance.
Okay, thank you.
Yeah. Okay, so now we have all those raw values for every model, then we can create our adding the CP and the error. This is a cross-validation error, by the way. Cross-validation errors to our hypergrid, so we can see each combination of attributes and their performance. So 144 trees for every tree. This is our minimum split and the maximum depth. This tree was sorted by arrow, by the cross-validation arrow, so we can see that this tree is the best performing tree. The next tree, very different. Could be different. We don't know yet. Has very close, but different cross-validation errors. So this is a way that you can pick up you don't actually have to always pick the minimum error tree. If you have two trees that have very similar cross-validation errors, you want to pick up the smaller tree, even though if its error is slightly greater than the other one. because for the robustness, the simpler is always better in machine learning. So we optimize. Then we can use these parameters that we have created to use information gain to build another tree. And we'll get the score for those tree. Yeah, well, this tree performs a little bit better than the earlier arbitrary tree that we created. This is 57% accuracy. Questions?
Yes, yes, I have a question.
Yes.
Can you scroll down on those 144 results?
Yeah.
The last column is which error? Is it the cross-validation error?
Yes, cross-validation error.
So which means that, okay, so, but so here the cross-validation error is 90. Okay, I see. Okay, never mind.
Yeah.